Okay, let's implement Newton's method. Newton. Okay, let's see the slide for the constraint we need to solve. Okay, so there is we are working on a linear hypothesis here. As linear hypothesis. So coefficient A and B. Okay. And plot get function const plot x. So ax plus b return. Okay. So and we can define error function. So plot error 0 was what was that? Let's go to the slide. So 0 1 0 2 1 0 1. So we have function f dot get f x minus let's do this. Y target was 0 minus and square and 1f, right? So this is the squared error function for first constraint, and let's do it for second constraint. So let's read the 1.5, 1.5. So 1.5, 1.5, 1.5. So total error can be defined in this way: 1 over 2 E0 plus E1. So we want to minimize this error. So we can use gradient descent method. Or to obtain the dA, which is equal to the E0 over dA plus the E1 dA A plus, right? And obtain the E dB, the E0 dB plus the E1 dB, and use them to update A and B. So A actually minus running rate dE dB. So this is the gradient descent method. And let's just skip this. And well, we can use Newton's method. Okay, for this we are going to use eigen library. 안 깔렸나 본데? Just eigen 3. eigen 3. 이거 안 뜨지? 있는데? 아, 86이라 그래. Okay. Okay, let's use eigen library. Eigen, right? Eigen. Source. Okay, let's go to the tutorial of eigen library. Okay, documentation, then 3. Let's go to getting started. Okay, so eigendance. So the reason why I use eigen library is that, well, TensorFlow is built on this library, eigen library. So TensorFlow internally uses eigen to define tensors. So I like it. Okay, so for Newton's method, first we need to define some matrices. So okay, here first we need to define gradient E. Let's go to here. So this is gradient round E over round A, round E over round B, round E over round A, E over round B. So we can reuse it. dA. Okay. Okay, and let's use let's define an error function here. So get error const float x const float y target. So const float f is get fx, right? And y target minus f minus f. Okay, so this is the error function. And we also need gradient of a error. So get d e d a maybe. So let's copy it. So what was that? So y minus ax minus b minus x gradient. So let's y target minus a x minus b minus x, and minus 1 for the b. Okay. So dE dA is f dot a for let's go back to the slide and see the given constraint 0, 1, 1.1, 1.1, and 1.5. 0, 1, so 0, 1 plus f get dE dA 1.5, 1.5 dE dB f dot get dE dB 0.0 dE dB. Okay. Okay. Well, we can use const then. Const here. Okay. So we can define gradient E matrix. So let's use eigenlibrary. So we can define a matrix in this way. Matrix XD. Should we need a namespace using eigen X. Okay. 그다음에 요게 D grad E matrix, and the grad E matrix actually column matrix. Is it a column matrix or a row matrix? It's a row matrix. Yeah, it's a row matrix here. So this is a row matrix. This is a column matrix. I think this is it. Let's double check. You may turn off the air conditioner. Okay. I think, yeah, this should be a column matrix. So this should have one column and two rows. And this is notation. So grad E 0.0 dE dA. Grad E 1 dE dB. Okay, and we may double check by printing it. Let's use cout. Cout grad E Okay, so we have a gradient. minus 1.5, 2.5. Was it correct? 아까 저렇게 나왔나? 다시 해보면 되겠죠? minus 1.5, 2.5. Something's wrong. Let's double check the code. Okay, so DEDA y target AX minus B minus X. Well, I think this should be correct. Okay. Okay, and next we can define a Hessian matrix. Let's go back to the slide here. Okay. So the definition of Hessian, here. So we need second order derivatives. So let's implement one more function, some more functions. So we need the two function, and we need to differentiate this one, and actually this is minus x. Right? No? What's that? There exists only numerical example. Okay, so let's do it. I think it's correct. And we also need the two and it's going to be minus 1. Okay. So actually the second order derivatives for scared error function is very simple with linear hypothesis. Okay. So const float the 2EDA2 is f get the okay. Right, const float the 2EDB2. Okay, and we also need float get D2E DAB, right? So from this, well, we need to differentiate this one more time, and it's actually minus 1. Simple, so simple. So const float the 2E DAB is AB, right? Okay, let's define matrix XD Hessian 2. So Hessian 0, 0 is the 2EDA2. Hessian 1, 1 the 2EDB2 H01 the 2EDAB, and this is 1, 0, right? Okay, let's go back to the slide. Okay, so delta A and delta B can be obtained by this process. So we need inverse H. Auto H is H inverse. Okay, right? And let's double check the result. Inverse. Okay, we have inverse matrix, inverse H matrix. So auto delta A and B. Actually, this is a column matrix. Should be minus inverse H dot dot gradient E. This means that this should be a row matrix. Column matrix. That it should be a column matrix. Okay, so minus inverse H times grad E. Okay, so let's check the result. FTD cout I think this should be 이게 컬럼 매트릭스가 하나 딱 나와야 되는데 2x2로 나오네.
그래도 2가
로우 매트릭스인가? 다시 바꿀까? 오케이. 원바이 그게 문제 아니고 그 둘 중에 하나 로우가 1인데 아니 컬럼이 1인데 로우 컬럼 1인데 봐봐 여기 00이잖아. 그럼 로우 컬럼 01 요건 것 같아. 1 okay. Okay, so okay, so A0, B0. We also need a matrix XD A0, B0 to 1. So A0, B0. Column is linear hypothesis. Where is F dot A? This is the initial condition. Row B, and we have delta A and B. So auto A B final is A0 B0 plus delta A and B final. Okay. So let's use the coefficient found here. So F dot A is AB final drop 0. f.b zero. Okay, and compute error one more time, right? Compute errors. Okay, this is final error. And this is the initial error. Okay. Okay. 에러도 커졌네. 어디가 틀렸나 보다. Okay, let's double check the code. So the slide is here. 해시한 미분이 틀린 것 같아요. 자, 이거 마이너스는 맞지?
그 위쪽에 정의했을
어.
클래스 안에
여기?
DA2가 X제곱이고요.
DA2가
X제곱.
X제곱이야? DA가 요거고,
마이너스 X가 안에 들어가서
아, 그렇네. 요게, 복잡하다. 자, 곱하기 요렇게고, 플러스 XX고, 플러스 BX. 그래서, 자, 요걸 A에 대해 미분하는 건가요?
네.
그러니까 X제곱? 오케이. 그 다음에, 또 틀린 거 없어요?
B 할 때도 같은 실수.
B 할 때도 DE, DB가 요건데 요거고 마이너스 플러스 이건 1 맞는 것 같은데? 아, 이건 1이라 마이너스 1이 아니고 1 1.0 이렇게. 그 다음에 AB도 그럼 0인데? 아니지. A를 AB도 AB는 또 마이너스 X 플러스 X 플러스 B X인데 요거를 B에 대해서 미분하면은 X네. 맞겠지? 오케이. Okay. So it gives the final error exactly 0.